So last time we talked about Dirac equation. So the Dirac equation has the following form. Gamma mu, partial mu, minus m, psi equal to 0. Okay? So here we have two spaces. So one is your standard physical space-time, so with x mu. And then we have another internal space, which is labeled by the index of the psi and the gamma, which I suppressed here. So psi should be considered as a 4 vector. So alpha equal to 1, 2, 3, 4. And the gamma mu should be considered as a matrix. Okay, 4 by 4 matrix. Okay? And so this space labeled by alpha, so this is called the spinor space. Okay. This is called spinor space. So you have to be careful. Now we have two spaces intertwined together. Okay, one is your ordinary space-time, and so this is a function of the space-time, but it carries its own index. Yeah, carries its own indices. And so this is the matrix equation. So altogether there are four equations here for each component of psi. Okay, for each component of psi. And yeah, so let me just write this a little better. So this is x. Okay, so let me call this equation 1, which I will use later. And this gamma mu, they are not ordinary matrices. They satisfy this condition. Gamma mu, the anti-commutator, with nu equal to q eta mu nu. So that means different gamma matrices, when their index are not the same, they anti-commute with each other. Okay, so if you you pass them through, you get the minus sign. Okay, so they anti-commute with each other, because when mu not equal to nu, the right-hand side is 0, and when you pass through each other, you get the minus sign. And the square of them, so gamma 0 square, you get the minus 1, because this is 0, 0, it's minus 1. And the gamma I square, you just get 1. Okay, so this is very simple. Yes?
When you say gamma I squared is 1, you mean like the identity, like the identity matrix?
Yeah, it's the identity matrix. Yeah. When I say gamma 0 square is minus 1, it's also minus times identity matrix. Yeah, exactly. And also, not all gamma mu are Hermitian. So the relation is that the gamma mu dagger is equal to gamma mu, gamma 0, gamma mu, gamma 0. Okay? So again, from here you can, yeah, so this is just a compact way to write its properties. When mu is equal to 0, and then you have gamma 0 times gamma 0 square is minus 1, and then you get the minus gamma 0, tells you that the gamma 0 is anti-Hermitian. And then if you take the index to be I here, and then you have index I here, and then when 0 and I, they are not the same, so they anti-commute. You can pass through this gamma 0, through this gamma I, you get a minus sign. And then gamma 0 square give you another minus sign, so you get a 1. So that means that the gamma I dagger equal to gamma I. Okay, so gamma I is Hermitian. Okay, yes?
Is there supposed to be like an I in front of like the derivative, or do we absorb the I into the gammas?
So in my convention, there's no I. So with this, so eta mu mu here is mostly plus metric. So some people, when they use, say, mostly negative metric, then there may be a I in there. Yeah. So it depends on your convention in defining the gamma matrices.
Okay, so minus plus plus plus, no I. Okay, got it.
Yeah. Good. Other questions? Yeah, as I mentioned last time, different conventions are allowing. So, but you just stick one convention, should be fine. Stick to my convention would be fine. Yes.
Sorry, how do we get the expression for gamma mu dagger?
Oh, yeah, this is just a compact way to write down that gamma 0 is anti-Hermitian and gamma I is Hermitian. Okay. Yeah, just this just compact. Yeah, just this is useful so that you can treat all gamma mu in the same way. Yeah. So that you don't have to always separate them. Yeah. Good. Other questions? Okay. So last time we also said you have many choices for gamma mu. But they are all physically equivalent, and so different choices, they are convenient for different purposes. Okay, so often we just pick one of them and depend on the problem we are. Yeah, so that comes with a little bit experience. So for certain problems, certain choices of gamma become more useful. Yeah, become more easier to manipulate. Okay, good. So now let's talk about the Lorentz covariance of the Dirac equation, which we started a little bit last time. So Lorentz covariance means that the equation looks the same in all Lorentz frames. Okay, so when you make a Lorentz transformation, so imagine you make go to another frame, you start with your frame defined by this x mu. So now imagine you go to another frame, which you make a Lorentz transformation. Okay, so the Lorentz covariance means it's your equation when written in this frame in terms of x prime mu have the same form. Okay, have the same form. So last time we talked about the scalar equations at the end, and another equation we have seen before is the Maxwell equation. Okay, so let me also very quickly mention for the Maxwell equation. So when you have a Maxwell equation, which is the story for the vector potential. Okay. So now, in contrast, remember for the scalar case. So last time, yeah, let me just write it down here. Last time we said for the scalar case, when you go to a different frame, the phi prime should be equal to, evaluate the new coordinate should be equal to phi x. Okay, so this is the transformation for a scalar field. But now, if you want to do Maxwell equation, so we have to think about how this A mu transform under a Lorentz transformation. And now A mu is a vector, it's a forward vector in space time. Okay, and so so that means that the A mu should transform also as the vector. Okay, so this means that when you go to new frame, A mu transform as lambda mu nu A nu x. Okay, so here not only, so when A mu evaluate a new position, can be written as a linear superposition of the value at your original position. And this linear superposition by itself is a Lorentz transformation because A mu is a vector. Okay, because A mu is a vector. And so that means just under a Lorentz transformation, the different components of A mu should also change under the transformation. Okay. So given this, so I will not show it now, just will take a couple of minutes, but you should convince yourself, try to check yourself, that the Maxwell equation, which can be written, so for example, as f mu nu equal to 0, this implies, okay, that the partial mu prime in the new frame, and then the f mu prime, f mu prime is obtained from this new A mu prime, and these two equations are the same, okay, are equivalent, just in one frame, and then when you go to a different frame, then you get this equation. So equation have exactly the same form, okay, but now it's in the new frame, okay. Good. So now let's go to Dirac equation. So now go to Dirac equation. So in the Dirac equation, again, this psi, we need to ask how the psi should transform under Lorentz transformation. Okay. But now this psi is a completely new object. So this is another. It's not like in the Maxwell case. We know this is a space-time vector. So you can easily guess how you should transform. Okay. So now this psi, this spinor space is completely new. Okay. So now we have to figure out how psi transform. Okay. How psi transform. So let's suppose. Okay. Suppose under Lorentz transformation lambda, like psi transform as follows: psi prime alpha x prime, because now again you evaluate in the new position, new frame. Since this carrier index, in principle, this can be a superposition in the you can mix them in the internal space. Okay, in principle, we can have form like this. Say for some matrix S, okay, which depend on lambda. Okay. So in principle, you can have a transformation like this. Say when you evaluate a new position, it's given by the value at the old position, but now you can make some rotations in the internal space, just as here for the Maxwell field. Okay, just as here for the Maxwell field. So except, and so suppose this, and then the Lorentz covariance would be the statement, say for some. For some matrix. And then the Lorentz covariance then is a statement is the statement starting from 1, from equation 1, you should be able to find, go into the new frame, you have an equation like this, gamma mu, partial mu prime minus m psi prime x prime equal to 0. Okay? So you should get an identical equation, not let's call equation 2. You should get an identical equation, but now everything is in terms of prime. Okay, everything in terms of prime. So why I emphasize the gamma mu does not change despite a carrier index mu, because gamma mu is just some constant matrices. Okay, just it's just 4 matrices. It does not transform under any space-time transform. It's not dynamical variable. It does not transform on the space-time transformation. So gamma mu does not change. Okay. Good. So now the question of the Lorentz covariance, whether the Dirac equation is Lorentz covariant, boils down. Okay, whether we can find such an S. Okay, which whether, yeah, the question is, can we find such an S? Okay, so if we can find such an S, which this is true, then we say the Dirac equation is Lorentz covariant. And this is how the Dirac field should transform. Okay, so this psi is normally called the Dirac field. Okay, and this is how Dirac field should transform. So psi is often called Dirac field. It's also often called spinor field. Okay, and it's also often called Dirac spinor field. And anyway, and then that should be the way how it's transformed. Okay. Yes. Yeah.
So why did we transform both in this case?
Yeah. No. In this case, so when you talk about transform of the scalar field itself, of course, it's just phi go to phi prime. And because that function changes. Okay, that function changes. But here we are asking about the form of the equation in the new frame. And so when you go to the new frame, your function form change, but your coordinate also change. So that's why you need to, when we say the covariance, you need to evaluate your new function in the new position. Yeah. That means they look the same in different frame. Yeah. Yes.
So should I think of S as the representation of lambda in this spinor space?
Yeah, exactly. Good. Exactly. That's exactly the right mathematical language to talk about this, which we will mention later. At the moment, I didn't want to use mathematical language. Yeah. For those people who are familiar with group theory, indeed. So this S would be the representation of the Lorentz group in the spinor space. Good. Okay, so now let's try to find this S. Okay. So before do that, let's first write what is a partial prime x mu. So recall, partial prime mu should be partial x prime mu. This transform the new coordinates. And from that transformation, you can easily figure it out, just chain rule. So this is the same, equal to partial x mu and lambda minus 1 nu mu. Okay? So this is very easy to figure it out because they have to be the x mu multiply the x. Partial x mu have to be a singlet, so this transform as an inverse matrix. So this implies that the gamma mu, partial mu prime, should be equal to lambda minus 1 nu mu gamma mu partial nu. Okay? Let me just write it better. Okay? So with this preparation, then we can try to see whether we can find S from this equation. Okay. No, yeah, find this equation from 1. So what we can do is that let's multiply the equation 1 from the left by S. Okay, so let's imagine we multiply S, such a matrix. Again, I always just suppress the spinor indices and just write in the matrix form. So let's just write gamma mu. So take that equation 1, we multiply by S. Okay? So we have two terms here. So this is a matrix in the same space as S. Okay, S acts in the same space as gamma mu. So we cannot easily commute here. Okay, normally they don't commute. But M is a constant, so we can pass S through here. Okay, we can pass through S here. So we can rewrite this equation as follows. We can write it as S gamma mu S minus 1 partial mu minus M S psi 0. Okay. So for M, I just passed S through. But for this term, I just inserted S minus 1 and S, and so yeah, it's the same. Okay. So now we can use this equation in here. Okay, because S times psi just equal to psi prime x prime. Okay. So now we get S gamma mu S minus 1 partial mu minus M psi prime x prime equal to 0. Okay, we just use that equation. Yes?
I'm a bit confused how you can pass S through partial mu, because given that partial mu acts on psi, then it has to have a representation in this inner space of that.
Yeah. So that's the key I emphasized earlier. So x mu and psi alpha, they're in different space. So all this S and the gamma, they're all constant. They don't depend on spatial location. And so partial mu does not act on S. Yeah, for partial mu point of view, S is just a constant. It's a space-time constant. It only rotates psi at the single point. A different component of psi at the single point. Yeah. Good. Okay, so now we have this equation. So now we can compare this object with this object. Okay. Yeah, in particular, this object is equal to that. Okay. So we conclude that 1 goes to 2 if S gamma mu S minus 1 equal to this object, lambda minus 1 nu mu. I think I'm messing up a little bit notation here. Gamma mu. Yeah, I think my index is a little bit wrong. Let me just make sure. Here is a partial nu. Sorry, here is partial nu. So I need to exchange the mu and the nu index here. So mu and the nu, then gamma mu. Okay. So this has to be equal to that. Okay, so this has to be equal to that, and you need to compare partial nu with partial mu. You have to exchange the nu and the nu here. Anyway, so this is the equation we have to satisfy. Okay. So we have to find a matrix S which acts on gamma mu. Gamma mu is some bunch of matrices, and give you like this. So as if the gamma mu actually, when you act on S, as if gamma mu transform as some Lorentz transformation. Okay, yeah, inverse Lorentz transformation. Okay, so we need to now let's try to find this S. So to do this, we use a trick which we have been using before. So how would you approach this problem? Good. Yes. Just do infinitesimal transformations. Okay. So once you know how to do infinitesimal transformations, then you always know how to do finite ones. And infinitesimal ones, it's much easier to do. Okay. So now again, we consider lambda nu close to identity. Okay, so that means we write lambda mu nu as delta mu nu, which is the identity, then plus omega mu nu, and take the omega to be small. Okay. And also remember, previously we discussed that omega mu, when you know the index, is actually antisymmetric. Okay. And this is infinitesimal, so we take this to be infinitesimal and work everything to first order in omega. Okay. Work everything to first order in omega. So similarly, the lambda minus mu nu just equal to delta mu nu, just give my minus omega mu nu. Okay. So yeah, just to leading order in omega expansion, the inverse metric is just given by that. So now we can try to so since the S, so on the right hand side, when lambda is close to the identity. Okay, so the right hand side is just the gamma mu. Okay, just the identity does not do anything, just gamma mu, and then plus something proportional to omega. Okay, then that means that S must also have, when lambda is close to identity, means S must also have the structure to be identity and proportional to something linear in omega. Okay, so the S must also have this structure. Yeah, let me just don't write the index, just directly write as identity. And then it should be something proportional to omega mu nu. Okay. So from convention we write this way. So it should be linear in omega mu mu and sigma mu mu. So sigma mu mu are a bunch of matrices. Okay. So remember, S is a 4x4 matrix. And so omega mu mu is just some number. Okay, just some number. So this will be a bunch of 4x4 matrices. So for each omega can, in principle, independently multiply some matrix. Okay, so this is the most general way to expand this linear order in omega. Okay, so this sigma is essentially just the first derivative of S with respect to each omega mu. Okay, and this I over 2 is just convention. And similarly, the inverse is just corresponding. You change the sign here to leading order in omega. Okay. So yeah. So I emphasize each sigma mu mu is a matrix. Okay, should be understood as some matrix. Okay, in this spinor space. Okay, so now you just need to plug in this equation, plug in this S and S minus 1 into this equation. Yeah, just expand both sides to order omega. Okay, and you equate the coefficients. You equate the coefficients. From that way, you determine the sigma. Okay, so let me call this equation star. Yeah, let me just call this equation 3. So then to order omega mu mu to linear order, then equation 3, when you expand on both sides to omega, to order of omega and equate both sides, then you find the following equation. This is just a couple of lines algebra, so I urge you to do it yourself. So given by I, commutator lambda rho gamma mu equal to eta lambda mu gamma rho minus eta rho mu gamma lambda. Okay. So you get this equation. So the left-hand side is very easy to understand. So essentially, you just, whenever you have a commutator, for people who have done this, Baker, Hausdorff, etc., the first order, you always get the commutator, okay? You always get the commutator, so that's where this commutator comes from. So the right-hand side, when you expand this, essentially you just get omega mu mu, because we have to lower the indices, okay? So you have some eta here, okay? You have eta here, and yeah. So that's how you get the right-hand side, okay? The reason you get 2 terms because it should be antisymmetric in the yeah. Good. So now it just boils down to solve this equation. So if we can find sigma satisfy this equation, and then we are done. Okay, and then we are done. So yeah, of course, this is now you do by trial and error. Okay, now you do by trial and error, and the bottom line is that there's a solution. Okay, so let me just write down the solution, and the nice thing about other people found the solution is that you can just check it. Okay, so you can check this quantity. This solves the equation. Okay. Okay, so just you can plug this. So this is the commutator of gamma lambda and gamma rho. You plug into that, then you just evaluate these gamma matrices, okay, and use this kind of equation over and over, and you will find this is satisfied. Again, I will leave it as exercise for yourself, okay, and as exercise for yourself. Yes.
That's how you get this lambda inverse.
Yeah, yeah.
Then the last thing is now actually this gamma is transformed, and it's not partial mu transform. I'm a bit confused how it seems like you're linking a transformation in partial mu with a transformation in.
No. So here we want to match 1 and 2. Okay. So the step is we do how each equation from equation 1 we reach here. From equation 2 we just plug this into there. Okay, and so each equation have done one step, and then I equate them.
Right, but I guess what I'm asking is like equation 1 has partial mu transform, and then that's how you get your lambda inverse. And then in equation 2, you are transforming your gamma.
No.
Right?
No. You want to show this. You want to match this equation with this equation. Okay, this equation is derived from 1. So we want to derive. We want to find the 2 from 1. Okay, this equation 1. So I just slightly rewrite equation 2 by inserting this transformation here. Okay, then I match them. Yeah. Other questions? Okay, good. Okay, good. So now, we can just immediately, so given this equation, and now we can immediately return the finite transformation. Okay. So with the finite transformation, so for each lambda mu nu, each finite, okay, you can obtain the corresponding omega mu nu, okay, and then this is also finite. And now we can just obtain the S by exponentiate this, okay? And then the corresponding S would be S equal to exponential minus I over 2 omega mu nu sigma. Okay, and the sigma mu is given by this one. Okay? So, and you can check yourself, this satisfies. You can check. This satisfies equation 3. Okay. Yeah. That's finite equation. Okay. Good. Any questions on this? Okay. Good. So now let me was there some okay. So now let's make some remarks. So then this S it just generates a Lorentz transformation in spinor space, okay? Because it only act on this alpha and beta. Okay. So sigma ij, or sigma mu mu, or according to our standard terminology, this is called the generator of the transformation. Okay, so these are the generators. Okay. So when omega nu, when the nu equal to spatial directions, and then that's corresponding to a space-time spatial rotation, okay, and the 0 I corresponding to a boost, okay. So remember, so that means for sigma ij, which is I equal to 4, gamma I, gamma j, this generates generators of rotations. So remember previously, say if you remember how we do the Lorentz transformation, the omega ij would correspond to the rotational angle in the ij plane. Okay, so you just rotate in the ij plane by angle omega ij. So then this just corresponding to the generator of the rotations. Okay, in the ij plane. So you can, because the gamma I and gamma j are Hermitian, we call that the gamma I is Hermitian, and then the sigma ij is also Hermitian. Okay, because when you take the dagger of these, I give you a minus sign, but the commutator give you a minus sign. Okay, the commutator give you a minus sign. So this is Hermitian. So that means that the S, which corresponding to a rotation, is unitary. Okay, so this is unitary. So this is a unitary matrix. Okay. So now let's consider the sigma 0I, which corresponding to the generator for boost. So this will have the form gamma 0, gamma I. So this is the generators for boost. In I's direction. Okay, in the spinor space. Okay. And now because remember gamma 0, when you take the dagger, you get the minus sign. So the sigma 0I, now if you take the dagger, you actually also get the minus sign because the So now it's an anti-Hermitian. Okay. So that means the boost matrices. Okay. So this is a boost transformation. So this is not unitary. This is not unitary. Okay. Okay. So this is not unitary. So in general, so normally, as we said before, normally when you do a symmetry transformation, the transformation is unitary transformation. But in this case, actually, this is a classical transformation. Okay. Here it's actually not a unitary matrix. Okay. So this implies So this implies that S dagger in general, for general Lorentz transformation, say which including both, say a rotation and boost, say S and S dagger is not equal to 1. Okay. Okay, S dagger S is not equal to 1. So this has very important consequences for example, for writing down an action for the Dirac equation. So far we only wrote down the Dirac equation, but we did remember previously we normally start with the action first, and then from the action we derive equation motion. But in this case, yeah, since this spinor is a completely new concept, we started with actually the equation. Okay, but now if we want to write down an action, which is by definition should be Lorentz invariant, then we should construct quantities which are invariant on the Lorentz transformations. Okay, and so this this property then become a key. Okay, yes.
So these are operators on the spinor space, and we're talking about like hermiticity and stuff, but like hermission is with respect to an inner product, and we haven't.
No. Here we are not talking about quantum mechanics. Here we're just talking about the equations, classical equations. We are just talking about their matrix. They're just matrix. We are talking about their whether they are unitary matrix or they are not unitary matrix. They're just ordinary matrices, 4x4 matrices. Yeah. Other questions? Okay. So that means psi dagger psi. Okay, so psi dagger is a row vector, and this is a column vector, and altogether this is a number. So this means this is not a scalar. So this transform under Lorentz transformation as psi dagger S dagger as psi. So that means this is not since this is not equal to 1, then this is not scalar under Lorentz transformation. Okay. Okay. So now we have to search a little bit harder to find the scalar. Okay. So yeah, in order to write the action, we need to find something which is invariant on the Lorentz transformation. So the easiest thing to think about is this quantity. Okay, because this automatically gives you a number. Okay, but this thing won't work. Okay, so we have to search a little bit harder. Okay. So to do that, let's we can get some hint from the following identity. Okay, so let's look at what this S dagger really is. Okay. So let's look at the property of S dagger. So recall that I think I erased it. Yeah. So let me just write it again. So gamma mu dagger equal to gamma 0, gamma mu, gamma 0. Okay. So now let's try to find what's mu dagger. So let's write mu dagger in the uniform. So even though we wrote it separately, so you can easily check yourself because of this property. So this is just given by minus gamma 0, sigma mu, gamma 0. Okay? Because this is just a commutator, so you can easily work it out that you just get this. Okay? So now we can find what S dagger. So S dagger is equal to the exponential 1/2 I omega mu mu, then sigma mu dagger Okay? And then this is equal to I over 2 omega mu mu minus gamma 0 sigma mu mu gamma 0. Okay? So now, if you remember, gamma 0 squared is equal to minus 1. So whenever you have such a situation, and because gamma 0 squared is equal to minus 1, then you can actually take the gamma 0 outside the exponential. So this is actually equal to minus gamma 0 exponential over 2 gamma 0 mu mu sigma mu mu. Okay. So if you just think you do a Taylor expansion of this exponential, and then when you take the power of this, then for each term, the gamma 0 at the end will pair with the gamma 0 at the beginning of the other term, and then they give you minus 1. Okay? And then you have only the first gamma 0 and the last gamma 0 left. And because that gives a minus 1, that changes this minus sign to a plus sign. Okay? So you just do a Taylor expansion, you will find here. Okay? It's Taylor expansion, find here. And now we find the nice relation. So we find that this is just minus gamma 0, and this is just equal to s minus 1, s gamma 0. Okay? So we find that the s stagger is actually minus gamma 0, s minus 1. Then this tells us, okay, from this property, okay, tells us that this quantity, psi dagger gamma 0 psi, should transform as a scalar. Okay? So now let's take a look. So this when you do a transformation, so this gives you the psi dagger, s dagger, then you have gamma 0, then you have s psi under the Lorentz transformation. Okay? And now you plug this into plugging s dagger equal to this into here. Yeah, you just get minus psi dagger. So this is gamma 0, s minus 1, gamma 0, then gamma 0, s psi. Okay? So this gives you minus 1, cancel with the 1 here. And then s1 cancel with s minus 1 cancel with s. And then you have dagger, gamma 0, psi. Okay, so this actually it's Lorentz invariant. Okay, so this is Lorentz invariant. So now we find a nice Lorentz invariant quantity. Okay. So since we use this all the time, so it's convenient to introduce a new notation. So now I introduce convenient to introduce we call psi bar equal to psi dagger. So here it's all just class. This is dagger and it's all just matrix manipulation. Okay. Right now we're considering a classical theory. And so it's convenient to introduce object like this. Okay? And then we know that then psi bar, psi is a scalar. Okay, so that thing just becomes psi bar and psi. Okay? So it's convenient to work out the how psi bar transform by itself. Okay, so you just use this relation, so you can check yourself. Okay, so exercise for you to check yourself. On the Lorentz transformation, psi bar x is equal to psi bar prime x prime. Okay, so if you go to the new psi bar prime x prime is equal to psi bar x s minus 1. Okay, so you can easily check yourself this relation. Okay. Similarly, using this transformation of gamma partial mu, you can also check that the gamma mu partial nu prime psi prime x prime equal to s gamma mu partial mu psi. Okay? So you can also check yourself or check this equation. Okay, so yeah, just by using these properties of S stagger, this you don't use you don't need use property S stagger. Just use the how partial mu prime transform and how psi transform, and then you can show this is true. Okay. Good. So this gamma mu partial mu will appear a lot because this appears in the Dirac equation. So it's convenient to introduce a new notation. Say gamma mu partial mu we define to be partial slash. Okay. So essentially anything slash corresponding to that thing contract with gamma mu. Okay. So, and then this equation then can be written as the partial prime slash psi prime x prime equal to s partial slash psi x. Okay. Great. So let me just mention one more thing you can work out yourself. Okay, so you can check. So these are all things you can check yourself. Okay, once you equip those transformations, you can also check that gamma psi bar gamma mu psi transforms as a vector. Okay, that means psi bar prime x prime gamma mu psi prime x prime is equal to lambda mu nu psi bar x gamma nu psi x. Okay. So if you view this whole thing as a vector, and then you see the quantity is equal to just a Lorentz transformation lambda on itself. Okay. So again, this is something just based on the transformations of S and the relations between different gamma matrices. You can just show that. Good. Any questions on this? Okay. So now with these preparations, we can now write down the action which give rise to the Dirac equation. Okay. So now we can write down the Dirac action. So the action which gives rise to the partial equation. So I will just write down the answer. It's very intuitive. So you have just essentially S equal to minus I d4x psi bar gamma mu partial mu minus m psi. Okay? So this is the answer. So yeah, so there are various things to uncompact here. So first, just based on those relations, based on this is a scalar, this is a scalar, and the transformation of this, okay, you can immediately see that this is a Lorentz scalar, okay, because it only involves two variables, one quantities, psi bar, psi with this m term, and then psi bar, gamma mu, partial mu psi, and that we already show here, that the transform as S. Yeah. So yeah, you can easily check just based on those equations that this is a scalar. Okay, and this is a Lorentz invariant. So the second thing is that this I here is to make the action is real. Because you can show if you take the complex conjugate of this, you actually get the minus sign, and so you need the I to make it real. Okay? And this minus sign, which cannot be explained now, which we will talk about it later, when we quantize the theory, and we see actually we need to put a minus sign here. Yeah.
In the definition of psi bar as like psi dagger gamma 0,
yeah.
It feels like we're singling out like the time dimension in like the definition, because like gamma 0.
Yeah.
Is that true? That we're singling out the time dimension?
Yeah, we are not really singling out the time direction. It's just due to the property that gamma 0 is not a Hermitian.
Okay.
Yeah, just because if you look at all this complication, it's just related to that this S dagger is not, yeah, S is not unitary, and the reason S is not unitary just because gamma 0 is not a Hermitian. Yeah, so you have to put in the gamma 0 in various places to compensate for that. Yeah, yeah. Other questions? Yes?
So I guess the action, if you wanted a Lorentz invariant, a Lorentz scalar, you could have constructed like some dot product of that object that transforms as a vector, right?
Yeah.
So the psi bar gamma, so that would be allowed in principle. I guess this gives the right answer, but that could have appeared in the action.
Which? Yeah, this appeared in action. Yeah. Yeah, so this is because this is a vector, so when this contracts with partial mu, that gives you a scalar, right? Yeah. Okay. Yeah, so that gives you a scalar. So yeah, you can understand that this is in both ways. This transformer, the fact this transformer vector is also related to here. Yeah, yeah. Yeah. Other questions? So yes.
So to follow up on that, if I contract that with itself, will give like another theorem, like maybe an interesting theory.
What?
When I contract that vector with itself.
Yeah. But then you will have 4 psis. So 4 psis will give you rise to an interacting theory. Yeah, that's right. Here I'm writing down a free theory right now. Yeah, indeed. Okay. So you can also see that this equation give rise to the Dirac equation. Just imagine psi bar is independent of psi because this is corresponding to psi dagger. So if you do the variation of this one, you just automatically get the Dirac equation. Okay. Then you can also easily check by integration by part. And if you vary psi, you get the complex conjugate version of the Dirac equation and acting on the psi bar. Okay. So now let me just say a few words on why you need the I here. So you can check. So here I'm listing some relations. Again, each of them you need to really write on the paper yourself, stare at it, maybe do a little bit derivation to get intuition about yourself. Okay, right now I'm just writing down those relations down. Okay, so you can also check yourself. That when you take the psi bar, psi dagger, okay, again just go through all this thing, you find it's equal to minus psi bar psi. Okay, so this is just 2 lines here. I will not write them explicitly to bore you. And similarly, you can check related to this the other term, that the gamma psi bar, gamma mu, partial mu psi. If you take the dagger, so here, so this one is slightly more complicated, okay? But you can still just you can just work it through. You find it's just equal to negative of itself. Then plus total derivatives. So this one is not exactly minus sign, but you have to throw away some total derivatives. So total derivatives, which give you, when you plug in into the action, they give rise to the boundary terms, but they will always assume the field vanishes at infinity. Okay. So that explains why you need this I, because when you take the complex conjugate of the quantity here, you always get the minus. Okay. Good. Any questions? Good, good. Okay, so now it's getting a little bit awkward because our printer today broke. So I didn't print enough of my notes. So now I have to look at my computer to remember my notes. So 1 second. Okay, good. I have to find the location. Okay, good. So any questions on this? Okay, no, okay. So now let's move to the next topic. So this concludes our discussion of the Dirac equation. So we have derived the Dirac equation, and also we have discussed how various quantities in Dirac equation should transform, and also the finally the Dirac action. Okay. So that, the next step, the logic next step is to quantize, to go to the quantum field theory. So right now, so far everything is classical. So now the next step is that we want to quantize this theory, and when we quantize this theory, we will see remarkably fermions. Okay, so we will see fermions, we will see Pauli principle, and but as we said before, that when we quantize the theory, we first need to the simplest way is to first find all its classical solutions, and then the classical solutions then become solutions to the operator equations, and then we can automatically quantize it. Okay, so then before we actually do the quantization, it's better we try to find all the classical solutions of the Dirac equation. And so it's not like a Klein-Gordon equation. We can just immediately write down the solutions. And the Dirac equation is a little bit more intricate. So we need to spend a little bit of effort to write down the to find all the solutions of the Dirac equations. Okay, so that's what we will do. Unfortunately, we are not going to finish today. And then we will have a long spring break. So I hope you still remember what we talked about today when you come back. Yeah. So this is. My computer doing a lot of things. Okay, so now we have classical solutions. Okay. So by construction, the Dirac equation has solutions. We know must be perpendicular with ikx with k squared equal to minus m squared. Okay, so this is by construction because we square it, we get the Klein-Gordon equation. So this k mu would be omega k and the k. Okay. But this is not enough because the Dirac equation, because psi have 4 components. Okay. So this just determines one factor of it, and we also have to determine its the behavior of all its 4 components. Okay. So so now that's what we are going to do now. So we will separate the solutions into 2 types. So one type is we call psi plus x, which corresponding to u kx, say expansion I kx. And another we call the psi minus x, which corresponding to vkx. Vk, yeah, sorry, no x. You consider minus ikx. Okay? So UK, VK, they're all 4 component spinors, okay, which have the same thing as psi because this is just some number. So because K have the positive frequency, okay, so this is some kind called the positive energy solution. And this is called the reactive energy solution. But it's the same thing as in the scalar case. There's not really, when we quantize the series, there's really no reactive energy excitations, okay? It's just a name, okay? So we call it the positive energy and negative energy just name. So later physical excitations always have positive energy, okay? So, and this UK and VK, they're all 4 components complex vectors. Okay? Yes?
So it seems like these psi should be greater by k.
Psi, yeah, so this is just the basis of solutions, indeed. Yeah, we should label them by k. Yeah. Good, so essentially you just, in the scalar case, you just expand it in terms of plane wave, and then you just get some constants. So here is that ability to integrate, we have a vector, now we need to solve these vectors. Okay, so our goal is to solve these vectors. And then you just plug them into the Dirac equation. Okay, just plug these 2 into the Dirac equation, and then you get the equations for the UK and the VK. Okay, and I will also suppress the K in the U and the V. Just for rotational simplicities. Okay, so when you have the gamma mu, partial mu minus m, psi equal to 0, you just plug psi plus minus in, and then you find the following equations for u. Is you get ik slash minus m u equal to 0, and ik slash and the minus. Yeah, I think let me just double check the sign. Yeah, indeed. So you get ik slash plus m v equal to 0. Okay, so you get these 2 equations. So our goal is just to solve those equations. Okay, and the k slash, just as defined before, it just defined as in the partial slash k slash equal to k mu. Okay. Good. So you can also work out their complex conjugate. So let me just write down the equations because sometimes they will be used later. So okay. So the u bar ik slash minus m equal to 0, the complex conjugate, and v bar ik slash plus m. Okay. So now let's try to work out the UK and the VK by solving those equations. So we do this by, you can in principle do it by brute force. So after all, these are just 4x4 equations, okay? 4x4 matrix equations, just linear algebra, okay? You can, in principle, we can all solve it. But the physicists often are lazy, okay? So we often still, even for the problem you can solve, we still look for shortcuts. And so in this case, there are two possible there are two possible ways we can do, okay? And so let me describe both ways. Actually, I think we only have time to describe one way. So to find the explicit form of U and V, so one simple thing to do is let's just consider in the simple case, say consider the particle is at rest. When the particle is at rest, then omega is just equal to m, and then k equal to 0. Okay, and then that equation just become I m gamma 0 minus m u equal to 0, and I m gamma 0 plus m v equal to 0. Okay? I think, do I? So yeah, I think let me. Oh yeah, sorry, I should have a minus sign here because is the k upper index. So is the k upper index equal to omega, then k lower index equal to minus omega. Okay. And here, when we contract with gamma 0, we use the lower index, so we have a minus sign here. Okay. So essentially, this just become, so m can be cancelled on both sides. So essentially, it just become the I gamma 0 u equal to minus u, and I gamma 0 v equal to v. Okay. So this tells you just tells you essentially gamma u is the eigenvector of u and v. They are just essentially the eigenvectors of gamma 0. Okay, they're just eigenvectors of gamma 0. Okay, and so let's just now to write them explicitly. So now let's use the explicit representation of gamma matrices. Yeah, let me just copy this. So now let's use this representation with the gamma 0 is equal to I0, 0I minus I, and then gamma I is equal to 0, I sigma I minus I sigma I, 0. Okay? And then now if you plug in this gamma 0 into those equations, and then you find the equation for u and v become very simple. For the u, just become 0, 0, 0, 1, u equal to 0. So again, this is 2x2 blocks, okay? Because this here is 2x2 blocks. And for v, just the 1, 0, 0, v equal to 0. Okay? So that means you can just take it to be the upper. So that means the solution of this equation so that means that the solution of this equation for u, so now let me write the upper index 0 means that this is for the 0 momentum. So here we can just choose to be psi 0. So psi is some arbitrary 2 vector, okay? For V, we can just choose the lower 0 eta. Okay, so psi, eta are arbitrary 2 vectors, two complex vectors. Two vector, 2 component vectors, 2 component complex vectors. Okay, so once you have U0 and V0, and we can choose a basis. For example, U0, 1 equal to 0, 1, 1, 0, 0, 0, and U0, 2 equal to 0, 1, 0, 0, and similarly for V0, 1 and V0, 2, okay? So you can choose to be here 1 and okay, so you can just choose as a basis, you can just choose to be there. And now once you have once you have the vector at k equal to 0, for general k, what do you do? Yes.
Lorentz boost.
Yes, just do a Lorentz boost. So below the matrix S, and then you just, for the general k, you just S U0 and the VK S V0. Okay? And then you can find the behavior general k. But this is easily said than do, okay? Do this actually is not quite easy. Okay, even though this sounds like a great idea. Okay, let's find the 0 momentum and then let's just do a boost. That, but this step is still a little bit tedious. But it's still it's doable and a little bit simpler than solve the original equation by brute force. Okay, but there's again still a lot of simpler method, which you can actually just guess the answer. You don't have to do any calculation. You can just guess the answer, guess the solution for the full equation. Okay, and I think we don't have time to talk about it today, and so we will talk about it next time. And yeah, so hope you still remember what we talked about today when we come back, and hope you have a good spring break. Yeah.